So if we take a look at an example here, let's go ahead and look at this. So we have an old school looking microwave here. Doesn't really look like a microwave, but that's a microwave connected to one of the outlets. Then we have a toaster and a blender connected to a splitter. So this is a splitter with 3 outlets on it. And what we're going to see is this. First of all, inside your house you have a circuit breaker with very minimal resistance. And what a circuit breaker does is it senses a very high current. If there's a really high current in the circuit, it will trip the circuit breaker and it'll open the switch in order so that your circuit doesn't have a short circuit in it. So it doesn't start to cause a fire. So a circuit breaker is really a safety feature. So that's all that is there. Now what happens is this. We'll see that the flow leaves the positive terminal. And it flows here. We look at the positive flow. And what happens is soon it breaks off first. So it breaks off into a microwave portion. This is the first outlet. And then this part goes to the second outlet down here. This is really one outlet that's been broken into 3 little prongs. So one part of it goes to the microwave. That's fine. But then the other portion goes into this part here. And what we'll see that really, this here is like a branching off. So this branch here and this entire branch here are in parallel with one another. But if we were to really just zone in on this section right here and forget everything else going on, what we'll see is that these 2 resistances are actually in series with one another. And it's not obvious right away, but it actually is true. Because the current is flowing here, and what will happen is the current will go through here, hit the toaster, come back around, hit the blender, and then come back through. So what we're going to see here is this is a little mini series circuit within a parallel circuit. So really we could simplify these two, and 41.1 plus 16.9 would give us 58 ohms. So in reality we could draw this circuit like this. Oops. And that's what this would look like, obviously, with the circuit breaker in place. And what we would have here would be, again, as we just stated, a 58 ohm resistor. Again, the sum of these 2 resistances, because remember in series it's a sum law, with this 8 ohm resistor as a microwave. And then what we'd have to do to simplify this parallel portion of the circuit would be to use our reciprocal law and say 1 over 8 plus 1 over 58. So what we're going to see is that what we really want to do is break down these circuits into series and parallel parts and simplify everything in series, then go to our parallel portion, simplify everything in parallel, and hopefully we'll be done there, or maybe we have to go back to series at the end. So let's take a look at an example of a circuit that's a little more complex than this. So in example 1, we're going to determine the equivalent resistance of this complex circuit shown, and then from this we're going to find the overall current in the circuit. So step 1 would be to redraw the circuit as a group of resistors alongside of one another. So what I would say is, think about it this way. Imagine there wasn't a battery involved and we just cut it straight there. We cut the circuit out, cut the circuit with the wire snippers, and then open this up. What would happen is this would look like this. You'd have the 3 ohm resistor, then you'd have the 6 ohm resistor, then you'd be branching off as we're showing up here. Here's the 4 ohm resistor. Up top we'd have a 6 ohm resistor here, a 2 ohm resistor here. They'd branch back together, and you'd have the 1 ohm resistor here. Okay, so again, we're taking this and opening up the flaps in a sense. So this would be the point where we cut it, right? We cut it here and we cut it here, or we simply just cut right there. And what this does is it allows you to see it a little bit easier to simplify. And now what we're going to notice is this. These 2 resistors are in series, so right away we can start by just using our sum law and say that's just a 9 ohm resistor, really. So what we've done already is replaced that first part. Then we'll see that these 2 resistors are also in series, so we're going to replace them with one resistor of 8 ohms. The bottom is still 4 ohms, and then they branch back together, and we have a 1 ohm resistor. Now, we can see that we still do kind of have some things that look like they're in series, but this little mini parallel part in the middle has to be taken into account for. So this parallel portion of the part, we have to use our reciprocal law. And we have to say, well, to simplify this, we can say that 1 over the equivalent resistance equals 1 over 8 plus 1 over 4. Well, 1 over 8 plus 1 over 4 is really 0.375. That equals 1 over Req. So then Req, or the equivalent resistance, is the inverse of 0.375. And that is equal to 2.6 repeating. So the equivalent resistance of these 2, rewritten as one resistor, would really be approximately, and I'll round to 2.7 ohms. So now what we have are really just simply 3 resistors, 9, 2.7, and 1. So if they're all in series now, as we can see, we can just simply add the 3 together and make the circuit look like the following. One resistor of 12.7 ohms. So let's redraw the circuit that we started with. And we'd have a 9-volt battery, as we had here, with just one resistor of 12.7 ohms. Now, with that said, once we've calculated the equivalent resistance, we can again use Ohm's law. V equals IR. This is the equivalent resistance. This is the total current. This is the total voltage, or the voltage supplied by the power source. So we want the current, so let's solve for I. So V over Req equals I. So the voltage of 9 over the Req value of 12.7 gives us a current of 0.71 amps. So that's the current through the entire circuit.